even worse than I expected. Okay, I guess we should start. As I was just saying, I'm feeling less than robust today, so let's see how this goes. Since on the exams, I was just saying, we'll get those back as soon as we can. I don't have the key quite done because of how I felt over it. So we'll get that done soon. I think 5 or 6 questions are already graded, so I just have to get them done. Try to get them done in a week. It's a holiday, so we'll try to have them working about it, at least posted on Blackboard as soon as I can. Because this exam was on Thursday, right? Yeah, I figured you kind of forgot what we were doing, so I should reset the stage a little bit here. So I thought I'd just go back and recall what we're doing and why we're doing it, and sort of how we set it up, and then we'll go on to the newer stuff. So we're starting the chapter on economic growth. My plans are we ought to be able to get most of the way through. Attendance always improves after I say that. We're going to get most of the way through chapter 11 today. I'm not going to finish it no matter what, because there's some parts that I need to take notes on yet. We'll get most of the way through. And then I plan to go through chapter 12 next week. If we finish before Thursday, we very well may. There's the parts I want to cover, then I'll just review and do something else. So the coverage will go through chapter 12, period. Just in case that's how it works. We're on chapter 11. And we skipped chapter 9. I wanted to get back to it, but we talked about almost all the issues in there one way or another, so it's not going to be fair. Okay, so we're trying to figure out how economic growth is determined. And in this chapter, we're looking at the effect of capital accumulation, more and more capital, given that we have technology constantly. We're just adding more shovels and more steam rollers, more factories, more trucks, all that sort of thing we think of as capital. And as we sort of keep adding this existing technology, what happens to economic growth? And in particular, we want to know how it's related to the savings rate. So a big thing in this chapter is going to be that the savings rate has a huge impact on the standard of living through its effect on capital accumulation. So one of the big points we're going to make is when savings goes up, investment goes up, and a higher level investment accumulates over time. It gives you more and more capital, and that expansion of the capital stock has a large effect, and according to the model, on the standard of living over time. And then if you go out and look at the world and say, okay, who has these savings rates? And this seems to explain things. And we're talking about this model because it seems to have some explanatory power in the real world as well. And so countries with higher savings rates ought to see higher standards of living, all else equally, of course. So where we started was, if you remember, one of our equilibrium conditions was that I equals S plus G minus T, and there's, it's a closed economy, so we're not worrying about net exports in our equation, and so we began with that, and then we just said let G equals T, so we can focus on private. So we want to focus on the private accumulation, private savings, and we'll bring government savings into it later. So this is I have this backwards. It should be T minus G. And as I tried to say government savings and saw it was actually a deficit, and that was clear. You might just want to put a minus sign there, either way. So we're going to just shut down government savings, taxes over spending, and focus just on private. So this is the IS curve. That's where it gets its name. Okay. So nothing new so far. Just starting with our basic equilibrium condition. Now we start making some assumptions for this chapter. Let's let savings be S times Y. So this is the savings rate. This is that thing we want to focus on. This is what we want to know how it impacts the economy. And 0 is less than S is less than 1. If you could borrow from other countries, that might not be true, because you could consume more than your savings would be, never mind. Savings wouldn't be bigger than income even if you borrow. So let's just not even say that. So this, we're just asserting is savings. So it must be that I equals S equals SY. Since these are the same. And this is all stuff we did before. Then we started talking about capital accumulation. So then we said, well, how does investment, because this is going to give us investment, relate to capital accumulation? Higher savings rate, higher investment. How does that relate then to the accumulation of capital over time? As well, if you just think about it, K, T plus 1, K is capital. Marks 1 minus delta KT plus IT. That's that. This is also SYT right here. So that's going to tell us how savings gets to capital and how income changes get to capital. And this is the depreciation rate. Not the depreciation K, obviously, it's one of the rate. And this is new capital. That's what investment is. This is the new capital that comes into the world. So we take, yes, this is what's left over of yesterday's capital after depreciation. Delta's between 0 and 1 here, the depreciation rate. So this is what's left over after depreciation. That's available tomorrow, plus the new stuff. That's all that equation says. Yesterday's capital minus depreciation plus the new stuff. And the new stuff depends critically on S and Y. Either one of those is higher, you'll get more capital accumulation over time. Then we want this stuff in per person. So now we said, okay, we're actually doing it per worker, I guess, but same. In our model, it's the same. So we have K T plus 1 equals 1 minus delta KT plus S YT is our equation now. Then we said, okay, we want to talk about standards of living, and so we need to divide by the number of people, because that matters. When you're dividing stuff up, how many people you have matters. So divide by 3 or 4 for the same amount of stuff. Adding new people adds more output than you take. That's very well. Then we just said, okay, finally, let's bring that to the other side. So KT plus 1 over N minus KT over N equals, I'm going to switch this around so we don't get the minus sign in front. So that's just that capital accumulation equation. Very simple. This side is what? That's change in capital per person. That depends upon how much you bring on that's new and how much you lose. dropping the pen and see if I can hear it. Boy, they're quiet today. So then we wanted to graph this thing and find what's called the steady state, which is a sort of a way of talking about equilibrium, a dynamic equilibrium. So we want to just find that place where things are stationary. That's what equilibrium always means, no tendency to change. And so what would it mean for there to be no tendency for the capital stock to change? It's that the change in the capital stock is 0. So the steady state has to be where these two things are equal. Where the amount you add equals the amount you take away. That's stationary. This is the part you add, the new investment. This is what you lost to depreciation. Those are equal, stationary. So that's all we want to do, and we're going to do it graphically because you don't like math. So now we want to turn this into a graph we can use to ask what if S changes, what if this or that happens, and get answers really fast and easy to the graph. But it's just this, we just want to find where the change in the capital stock is 0. It's nothing more than what you add equals what you take away. So we need to find where these two things are equal. So we'll just graph them. So one equation will be, this is k over n here. And this is y over n, or whatever we're looking at. All those things. So this is just delta k over n. Then I did this the other way last time. Let me do it a different way. Then we just put in this s yt over n, and that point is where those things are equal, right? So that's the stationary state, steady state, SS. We're going to indicate stationary states, steady states, you hear both, with a star. And there's no need to put a T on it because it doesn't change. It's stationary. So it's the same every day. So we don't need a T. Now, we're actually mostly interested in the standard of living question. This is all just a means to get there. So we need to put the production function on here too. So what we can put here is just yt over n. Last time I wrote this as a production function, but it's just yt over n. This is some fraction of y over n. Right? S is between 0 and 1, so it just rotates this line down by a fraction. So then we can go up to here. That's y over n for every k over n. So that's y star over n. That's our stationary standard of living. So with that level of savings, that level of depreciation, those are the two key parameters here. S gives you where this line is. Delta gives you where this line is. There's k over n on this axis. This is S, F, k over n to the purest. What's actually varied on the axis is k over n. I wrote it as y because I think it's more intuitive, but if you want to write it properly, y equals f of x. I'm just writing the y instead of the f of x. That makes sense. So now that's it. So now we've got our basic set. And again, what matters is this S and this delta in terms of determining what the stationary state will be. So now you can ask both questions. What happens if delta goes up? Should be obvious, right? What's going to happen? You're not going to get as much capital accumulation, so the stationary state's going to move to the left, and you're going to get less. This goes up, the equilibrium will move down. If S goes up, what happens? This line rotates up, and you'll get a higher standard living. At some point, it flattens out. So let's do both of those. Oh, let's do something else first. Let's show, and we did this last time, I think, that you really will get forced to this point. So this really is an equilibrium. If you're not at it, there are forces that will bring you to that point. Let's try to show that. All right, so you have delta K over N, this S thing, S F K T over N, that's just Y. F of K over N, that's just Y. And again, this is a stationary state, K star over N. But let's start here. K T over N. Remember how this one works? So I think the book uses DC and D, DC and D, the other way around. D, C, B. It's points D and C that are important. So what does this point give me here? Well, that's depreciation, right? So at KT over N, the depreciation, which is point D, is less than, what's this give me? Investment. That's the new stuff. Is less than investment, which is point C. So what is happening to K over N in that case? If you're adding more, investing more, and you're taking away, it must be that the capital stock is growing in time. So, guys, this would mean that KT over N is rising over time. Because you're adding more than you're taking away. So you tend to move in this direction. Over here it flip-flops. This is C and this is D. And you tend to move in that direction. On this side, the investment is less than depreciation. So if this model is correct, there's a tendency for economies with no technological progress to simply hit a stationary state. That tells us something about the ability to grow for thousands of years, right? What's it going to take? Some sort of technological progress. And that's what chapter 12 is going to be all about, is that's really the key to growth. S gives us the standard of living, but we don't get constant growth out of that. It's still the case that lower S's or higher depreciations give you worse standards of living. But it's not the key to growth. Okay, now let's do the depreciation rates probably don't change that much over time. I'm trying to think why they would, but it's hard to think of a reason. Let's just ask. Okay, what happens? Let's just do, it's obvious, I think. Let's just do the exercise. What happens to the standard of living? You start out with one depreciation rate, delta naught. S, F, K over N, F, K over N. So that's our stationary state. And this gives us our standard of living. get those zeros. Since nobody's using the crappy colored chalk that I left in here for them, maybe I'll try. So what if delta goes up? That's such that. Never mind. Oh. Orange and yellow, that's all I have. So this goes up to delta 1 K over N. And the standard of living, K1 star over N, false. Phone's not ringing in class.
This is for the depreciation increase?
Yes. So if you destroy more capital every period, your standard of living falls. Again, it's hard to think why the standard of living would change abruptly over time, or not the standard of living, like examples of that. The depreciation rate. You might think of a war, something like that destroys your capital. That's a higher depreciation rate. You'd think it would lower the standard of living.
So like you do that with Hurricane Katrina hit or something like that, would that
Yeah.
essentially be the
Yes.
result?
Yes, that's a good example. So natural disasters would also have this same property, especially if it was a widespread sort of capital destruction. Certainly in that local area, you can sort of apply this too. Yeah, exactly. Other than those kinds of cases, I think it's hard to come up with why capital. I guess one reason is it might vary with the intensity that you're using it. And so if you're really pushing your trucks and your factories 24 hours a day and your output level is really high, then you might get a very high depreciation rate. But that's a short run fluctuation. When we're talking about long run economic growth, so you just average those over time. Anyway, savings is the one we're more interested in. So let's do that one. We'll do a lot of this after the graph. K over N, delta, K over N, S is 0. This really shouldn't pass horizontal, and I'm the worst artist on campus. So, this shouldn't pass horizontal. It shouldn't go back down. I'm not a good artist. That was a very nice one. And you have F, K over N, output. That's the production function. So you start off with that standard of living. Increase the savings rate. And according to this model, that would rotate up to S1 F of K over N, and you'll end up with a higher level of capital per person and a higher level higher standard. What is savings? The savings rate is going up, yes. So S1 is greater than S0. And so this just rotated up because savings went up. It's called the solo growth model. Partly what he got his Nobel Prize for. So when the savings rate goes up, you can't see it very well here, but you'll get economic growth for a little while as the standard of living goes up, but eventually you hit a new steady state. So one thing we're going to ask with our model later on is, how long does it take and how big is this effect in the data? Suppose the savings rate went up. Suppose the depreciation rate was 10%. When the saving rate goes up from 10% to say 20%, what effect would that have on the standard of living and how long would it take? Turns out it has a great big effect on the standard of living, but it takes decades to unravel, to occur. All right. But before we get there, we're going to do something else. A little out of order. Okay, so now the book says, you know, the government can affect the savings rate. One, it can save T minus G, or it can dissave and move you in the other direction. And so that's sort of forced savings. That's the amount the government takes in, it ends up in the banks, it goes out into investment, right? So when government takes in more money than they spend, they do what everyone else does, they put it in the bank, the banks loan it out, and you get more investment. So just like the private sector, the same thing happens. And they can also, through taxes, tax changes can reduce changes in this. So then what's the optimal, the best savings rate? And there's something called the golden rule. That's the optimal savings rate. Then we're going to ask, are we at the golden rule? No. Why not? And then we'll try to answer that question. The golden rule maximizes consumption. And so if we think the goal of sort of the standard living is to give people as much stuff as they can get, and there's some savings rate, it turns out, that maximizes consumption per person. That savings rate is the golden rule. To get there, though, say you're below golden rule, we'll write on this one. To get to it, you have to lower present consumption in order to increase future consumption. The idea is that the voters today don't like to reduce their consumption so people in the future can have more stuff. But the golden rule would say, do unto them as you'd have them do unto you, right? You'd want them to do what they need to do to reach the golden rule, and why doesn't it happen? So that's sort of the story we want to tell. There's this optimal savings rate, gives us the most consumption per person, we're not there. And it seems to be a political economy story that prevents, almost all countries seem to be below. All right, so we need to write down what consumption is. So the first thing we want to note is that when S goes up, consumption goes down today. But S up can cause C up in the long run. So this is the story I was just telling. Also possible, though, that S going up causes C down today and C down in the future. See, in this case, the future generations would want a higher savings rate to reach the golden rule because they'll get more consumption in the future. But if it takes 20 years, maybe, you don't care, you're alive today. This one, you want to reduce the savings rate because it makes everyone better off. So it depends upon which side of those two which one of those two situations occur. So we're going to make an argument. Let's see how it goes. Let's consider, if you will. You do if you want. If S equals 0, there was never any savings, always, and everywhere, and forever. Capital equals 0. Because investment's always 0. This means that investment's always 0. You never had an investment, you never had any capital. And y is k over n. So y over equals 0 and c equals 0. So if you have a 0 savings rate, it's always and forever. That's not so good. So also, suppose s equals 1. Well, y equals c plus I plus g, but it's all going to here. C would be 0. Because everything's going, I mean, that's, part of the argument trying to say, you've got 40% investment, so you don't get much consumption, as they're using it all for investment. Use 100% for investment, you've got nothing left for consumption. S equals 1 is 100% for investment. So there's nothing at all left to consume. Well, that's not good. So now we know that as we vary S, there's 2 endpoints. So what we want is consumption per person to be maximized. We want to look at S. Well, we know that S is 0, consumption 0. And we know that when S equals 1, consumption is 0. So, and we know it's not 0 in between. So there must be some point where it's a maximum. There must be some golden rule level of consumption. Or sorry, that's not C there. C's over here. This is S star. That's the golden rule level of savings. Sounds like there's some depreciation going on around here. So again, that's the golden rule. All right. So let's talk about the real world instead of all this lines in the chalkboard. So let's just talk a little bit about the empirical evidence, the evidence based upon real data. What does it tell us about these things? In most countries, and we'll look at this for the US a little later, S is less than S star. So mostly you're at a point like over there somewhere where S is too low, consumption is too low. So this is the situation where when S goes up, you take less consumption today, more savings and more investment. Consumption goes down today, but you get a higher level in the future because you move towards C star as S goes up. So when S goes up, in that case, C would go down in the short run today, but it would go up in the long run. But that long run turns out actually to be a long run. It's like going to be 20, 30 years. And so the problem, as I keep saying, and I'm sorry to be redundant, is that it appears that present generations won't sacrifice consumption for the future. Now, maybe there's another story, but that seems to be the one that most people want to tell. book says the savings rate in the US is about 17% since 1970. That seems high. I thought it was lower than that. They claim that's what the data says. All right. Getting a sense of magnitude. These are the titles in the chapter. Well, I sort of hope most of you had 311. I don't think it's pretty bad. But if you have, and you've seen a Cobb-Douglas production function, we're going to use one of those now because it's still parameterized this thing. And then we need an actual model now to look at things. So we want to ask two things. How big of an impact in the actual data, or if we put some numbers in this thing, how big of an impact does S up have on the standard of living? How long does it take to get there? And I asserted we were below the golden rule. How far are we from the golden rule? I'm going to sort of wave my hands at that one a little bit and send it to a table and vote if you're really interested. But we'll answer the other two specifically. So our general production function we just write as a function. Yt over n is some f of kt over n. Now we're going to use a specific model that we think sort of does okay at representing the data. You could probably do a little better if you worked at it. You could. But this is fine for our purposes. We're going to use this. We're going to start with this production function. Yt is k to the 1/2 L to the 1/2. The book uses square roots. If you like those better, they write it as y. Oh, these are kt's, lt's. Yt to the square root kt, square root lt. You could also put them under the same thing. There's lots of ways to write it. Whatever you like. Then we need to get it in this form, so we'll divide by n. So Yt over n is kt to the 1/2 nt to the 1/2 over n. I guess we aren't putting t's on those. I hope you know that. So that's kt to the 1/2 n to the minus 1/2. So we can write Yt over n is nothing more than kt over n to the 1/2. So that's what the Cobb-Douglas tells us. And I meant to say back here that it has constant returns to scale and diminishing returns to individual factors.
L disappears? Or you divided by N and over N?
Here,
Okay.
so. Oh, was I using L? Oh,
No.
I slipped into a different notation.
Okay.
L equals N. I'm so sorry.
Okay, I thought I was fine.
No, you're not crazy, I am. My fault completely. I don't like using it, I like L. Wait, got it.
So you want us to put L, or is it?
N, let's use N, because the book uses Ns,
Oh.
and otherwise we'll be using, it'll just confuse everyone. They use L for labor force.
Um,
Some books actually use N for the labor force, the number of people. So, this is N to the 1/2 over N is N to the 1/2 times N to the -1. Like bases add exponents. That's N to the -1/2, which is what I wrote there. And that's just, we got it. I think it's a little hairy at this point. Stick with it. There's a really simple result in the end. We have to get there. So let's go back to kt plus 1 over n minus, this is our change in the capital stock equation, was SF of kt over n, that's this thing, yeah, minus delta kt over n. So we're gonna sub here. And the PhD students tell me I go way too damn fast, so I'm trying to just pace around. Not go so fast. Not go so fast. There's so much I want to tell you. This is still terrible, but I'll get it all out. Function goes like that. Yeah, retention and speed. Yeah, really, you know. But then you can slow me down and do it. That makes it all okay. Now, I'm over here. Kt plus 1 over n minus kt over n is s times that. Did I mess you up by using square root instead of a half, anyone? That's just that. Oh, yeah, we're supposed to use that. Here it goes. Okay. Now we want to know what this tells us. So now we know the steady state is where those things are equal. That's going to give us a really simple result. So we haven't really done anything new. All we've done is take our capital accumulation equation and plug in a specific example of a production function. That's all we've done. Now let's look at the steady state. Where those two things are equal. So it has to be that s square root kt over n, I'm not really any t's on these steady states, but oh well. Delta kt over n. So now I just want to solve for k over n. And what you'll learn is that k over n, should I actually, yeah, I guess I should do it. What you have to do is square both sides and then divide by k over n. So we're going to square both sides. And then we're done, almost. Divide by k over n. Good news is, I don't have that much material left. We're never going to make it to 10 and 6 today. So just stick with it for a little while longer. I wasn't able to start doing this till about 10 this morning. I just as many notes as I could before my first class. Okay, so square both sides, divide. Every bit of this is laid out in the book, too. So you'll get s squared times k over n equals delta squared times k over n squared. Divide by k over n and solve for it. This tells you that k over n equals s squared over delta squared. And I skipped a step there, but just divide by k over n. That gets rid of this square. And then just move that into there. So surprisingly, capital to n just depends upon that ratio. It's a pretty simple equation. Now let's just do output. So the steady state output, that's actually a steady state. Y star over n is the square root of k star over n. That's our production function. So y star over n is just the square root of this. It's s over delta. So in this model, the standard of living reduces to a really simple equation. It's just s over delta. S goes up, it goes up. Delta goes down, it goes up. So if you start with a savings rate of 10%, so let S equal 0.10, 10%, and delta equal 0.10. That's a pretty common assumption for about what delta is. Then Y over N equals 1.0. So these are in subunits. It's all relative here. I can change this from pennies to dollars to whatever to change these units. So it depends on the units. But anyway, S, so that'd be the standard of living for those two things. Now let S go up to 0.20. What happens to Y over N? Well, it goes to 2.0. So that's a huge effect on the standard of living. The savings rate goes up by 10% in this here, and the standard of living doubles. Basically, the results, if the saving rate doubles, the standard of living doubles. Because it's just delta, it's homogeneous and real. It doubles. But how long does that take? And remember, it causes current generations to sacrifice. So if this doesn't happen very fast, it's unlikely people today are going to want to increase the savings rate to try to raise the standard of living in the future. And it's going to take a really, really, really long time. So this is the section called the dynamic effects. We're going to draw a graph of what this model implies about y over n over time. So we're going to increase S and use our capital equation, capital accumulation equation, which gives us kt plus 1 in terms of yesterday. Sort of iterate and see what happens to kt plus 1 over time. And if we put these in some sort of time unit, we can get a sense of how long it would take and how big the effect is. We already know how big the effect is, it doubles. And now we're going to see that after 10 years, you only get 40% increase in the standard of living. After 20 years, you get a bit more, so it's going to take a long time. So that's going to be the point we're going to try to make with the numbers. Then we'll have a graph at the end. So we're going to do this. S go up from 0.10 to 0.20. In China, it went up to like 40%. That should, over a long period of time, have a huge effect on the standard of living. It's something to be seen. Some of you know the numbers better than I do. That's what it is. In year zero, so year zero is when this happened. It all happens in year zero, 2001. Nothing happens. To capital. Since it takes a year for an increase in investment to cause capital to go up. Remember our equation that we're going to use right now is that, which way are we going to use this? K t plus 1 over n minus kt over n is s times kt over n minus delta kt over n. This is the investment part here. So investment doesn't turn into capital until the next year. And so in year zero, you don't get any effect on the capital stock from the increase in investment. The next year you do. But in that initial year, you just build it. It's investment first year, it comes active the second year. It's not capital yet. It's I. It'll be capital tomorrow after it's built. So in year zero, we'll stay at the steady state. Nothing happens to K over N. So in year zero, what you basically have is yt over n is still the 0.10 over 0.10. Standard of living hasn't changed yet in year zero because the capital stock hasn't changed yet. Now it's going to start growing. So we can use that equation to say, okay, that's year zero. Let's look at year one. K1 over n minus K0 over n must be S times K0 over n minus delta K0 over n. These are 1.0. And this is 1.0. So we have K1 over n minus 1 equals 0.20 times 1. Square root of 1. Oh, this should be square root of n. So 1/2 right there. That's the square root of 1 minus 0.10. That's the square root of 1. What you'll get if you work this out is k1 over n is 1.1. Now, we could keep doing that, but we're not going to because you're already losing interest and wondering why the hell we're doing it at all. So now let's just graph the thing and what would happen if we kept iterating. We could now find k2 over n minus k1 over n. We plug in, this would be 1.1, this would be 1.1, this would be 1.1, and we could find k2 over n. Once we have k2 over n, we can iterate and find k3, k4, and go out to k infinity. So if we do that, it'll look like the following. There's 2 graphs. These are drawn much better in your book. So this is the level of y over n, and this is the growth. And here's time 0 right here. We're going to start here at time 0 at capital size. Oops. And we start at 1.0, and we know we end at 2.0. So let's just put this asymptote here so we know what it is. Our standard of living started at 1.0. We increase the savings rate, and it starts climbing. It asymptotically hits the newer standard, higher standard of living. But if you go out here to the 10 years mark, it's only 40% of the way there. My graph's not to scale very well. It looks like you're actually, it's not so bad actually. 40% from there to there. And then if you go out to, yes. So it takes a long, long time. Now this is the growth, and it's going to look like this. You're going to start, it's basically the slope of this thing. You're going to start with a high growth rate in the standard of living, and then the growth rate gets smaller and smaller and smaller until it finally gets to the new steady state. You're at 0 again. The new steady state is 2.0. What you'd see in this model is for the first 10 years, growth would average 3.1%. So that doubling the savings rate would give you a higher growth rate of 3.1% in the short run. For the second 10 years, it'd be 1.5%. So the average for these first 10 years is 3.1, the next 10 years it falls, the next 10 years it would fall, the next 10 years it would fall. And eventually, remember, the S is just going up in that initial diagram. We're eventually going to get to that new steady state. This is how long it takes and how big the effect is. So the point is a simple one, right? It takes a long time. It's a pretty big effect, but it takes a heck of a long time. Okay, I have that much left, so it'd be stupid to break right now. So we aren't going to. Then we can bail early. I don't usually do this. Ding me if you want. Let me know, baby. Okay. This is just the U.S. savings rate. And I'm not even going to say anything here. I just want to, if you look at consumption per person, you can write it as output per person minus delta K over N. And you can show, and I'm just going to say see the book, there's a table in there where they show this pretty clearly. that for the US, C over N is less than the golden rule. And the book does exact numbers, but it's a big old long table, and it just seemed like too hard to present on the board. So, and the numbers aren't that important. So we're below the golden rule, and it's for the reasons. So all I have left in this chapter to cover next time is about 2 pages on adding human capital to this model. And then on endogenous growth, they call it. And it's just an introductory material. Then we'll go on to the next chapter and begin to look at technological progress with the same model, same sorts of tools. So, this video should be much easier to process because we are done.